Hello, Dr. Spencer, Dr. Singla, and Davide. We are Team 7, also known as Team Resupply. Today we will be presenting our final conceptual design for the NASA RASC-AL propellant resupply capability mission. Our team consists of Santino with structures and launch vehicles, Alex with power and propulsion, Takugo with ground control and communications, Kevin with command and data handling, and Nick with GNC and thermal. Nick will now talk about our mission requirements and constraints.
The request for proposal gives 5 major requirements. First, our mission must be capable of delivering fuel to a spacecraft in cislunar space. Asclepius will be delivering the fuel to a lunar distant retrograde orbit. Our mission must also be capable of fueling a Mars mission at every other opportunity starting in 2033. This gives 4 years and 4 months between successive missions. Our mission must also be capable of transporting both electric and chemical propellants. Asclepius will be transferring MMH, NTO, and xenon fuel. All onboard technologies must be ready for deployment by 2029. This is 4 years before the first mission. Team Resupply will aim for a test flight as a technology demonstration flight sometime in 2030. We must also be capable of delivering many metric tons of fuel to the target spacecraft. We will be supplying about 40 metric tons of fuel. Our mission will meet the requirements by performing the operations shown here. The target spacecraft will launch first and be placed into LDRO, where it will await for a fuel resupply. Asclepius will then be launched and deployed into a translunar orbit. Asclepius will then perform a few maneuvers to bring it into a lower LDRO than the target spacecraft. Asclepius will trail behind the target in this lower altitude orbit. The faster orbital period will allow Asclepius to catch up to the target spacecraft. At this point, Asclepius will begin its approach to the target spacecraft. The two will rendezvous in the higher LDRO, where Asclepius will transfer its fuel. Once all fuel has been transferred, Asclepius will depart from the target spacecraft. At this point, Asclepius will cease all station-keeping maneuvers. This will allow the Earth-Moon instability to send Asclepius out on an escape trajectory as its disposal. This will take a few weeks, which will allow time for secondary science missions. Once Asclepius is docked, fuel will be sent over at a controlled flow rate using feedback control. The fuel rate of transfer will be measured using pressure sensors in the fuel lines and tank to measure dynamic pressure. This information will be fed back in a feedback control loop to have a safe and controlled fuel transfer. The walls of the tank will have a maximum static pressure before damage or rupture occurs, which could be dangerous if unaccounted for. Because of this, an additional safety measurement of the static pressure will be taken to limit the output of the collapse controllers. This will be the pressure difference between the exterior of the spacecraft and the interior of the tanks. This will prevent the collapse actuators from overpressurizing the tanks if the commanded mass flow rate results in a static pressure that exceeds a safety range. And now Santino will talk about structures.
For a successful mission, Asclepius' structure subsystem must be able to store the propellants being transferred safely and without permeation losses, physically transfer the propellants to the target spacecraft, and provide space for all of Asclepius' necessary hardware and instrumentation. Asclepius' collapsible fuel tanks will be made of silicon rubber with phenyl, vinyl, and methyl molecules added to its polymer chain, otherwise known as PVMQ silicon rubber. In order to combat propellant leakage and degradation to the tank walls, each tank will be coated with a specific aluminum alloy that is compatible with the propellant being stored. Each tank will be cylindrical in shape and have an optimized radius and height that minimizes its surface area. The tank's piping will be made of the same PVMQ silicon rubber in line with the same aluminum alloys. It will also be able to deform so it can move with the tank wall as it buckles outwards and the docking module as it translates downwards. Carbon fiber hexyl AS4C structural panels will be placed at the top and bottom of each tank. These panels will be connected to actuators that will collapse. As a result, the panels will squeeze the propellant out of the tanks, through the piping, and into the target spacecraft. Each tank structural panel system will have 4 aluminum alloy 5454H34 telescopic linear actuators placed equal distantly around its perimeter. These actuators act as the dynamic mechanisms that cause the tank's collapse. Each consists of 5 cylindrical stages that collapse into a storage base and 2 connectors that insert into the top and bottom structural panels. In addition, each actuator will have a collapse rate controller to ensure that the top and bottom structural panels stay parallel during a collapse. Asclepius will feature a docking module made of aluminum alloy 1060. This module will route the silicon rubber piping through the NASA docking system interface that attaches to the target spacecraft, and it will also house the autonomous robotic docking arm that aids in berthing. Asclepius's command module will also be made of aluminum alloy 1060. It will contain all of the mission systems and sensors that control Asclepius, including all the hardware for command and data handling, power electronics and solar panels, communication hardware, and GNC instrumentation. To ensure success, the selected launch vehicle for the resupply missions must be able to handle Asclepius's weight, which is 72,812 kilograms, and size, which is 7.2 meters in width and 20.2 meters in height. In addition, it should have a launch capability beyond a LEO orbit, be launched on a date that minimizes future delta-V maneuvers, and be as minimal in cost as possible. The only proposed launch vehicle that satisfies these requirements is the Space Launch System Block 2. The SLS Block 2 has a maximum payload weight of 130,000 kilograms and a cargo fairing that supports payloads up to 10 meters in width and 27.43 meters in height, while its exploration upper stage can use a translunar injection to send Asclepius on an optimal lunar trajectory. While projected at $500 million per launch, this cost can be reduced by sharing the SLS's payload space. The first resupply mission has a launch date of January 1, 2033 at the Kennedy Space Center, as this date minimized the required delta-V for an LDR insertion in the STK simulation. In order to efficiently attach Asclepius to the SLS and also take advantage of the resources the EUS can supply, Asclepius will use a payload adapter that consists of a payload attach fitting and a payload separation system. Also, when Asclepius is loaded into the payload fairing, its hardware and instrumentation will be oriented in a way so that no obstructions occur. And now I will hand it over to Alex for our propulsion subsystem.
The functional requirements for the Asclepius propulsion system was to provide an adequate propulsion system that would allow Asclepius to complete its mission to LDRO, as well as providing a total delta-V and a translunar injection trajectory. STK-11 was used to develop a simulation of the type of translunar injection that resuppliers would like Asclepius to follow. The SLS will launch the payload into a translunar injection orbit. It will then take 6.5 days for Asclepius to arrive at its destination. Once Asclepius has reached its destination, it will perform an insertion burn which will place it into LDRO. The insertion burn will require a delta-V of 0.7 kilometers per second. Once Asclepius is in LDRO, it will then move forward to rendezvous with the other spacecraft. This orbit will not require station keeping for a total of 120 days, which will benefit our secondary science missions. Asclepius propulsion system will be using nitrogen tetroxide as our oxidizer and monomethyl hydrogen as a propellant. 2 million newtons of total thrust will be needed to produce a delta-V of 0.7 kilometers per second. 9 ASS-2 engines will be used to provide the necessary thrust. Now Takuga will speak about our ground control.
For ground control, 3 facilities must be identified: a mission control center, a spacecraft operations control center, and a payload operations control center. Each must have excellent communications with each other and have access to deep space network and be capable of handling autonomous docking and a scientific mission. All 3 facilities will be located at the Jet Propulsion Laboratory. This is because creating custom facilities will be too costly given the simplicity of the mission. Furthermore, JPL has direct access to the deep space network and has a long history of doing complicated unmanned scientific missions. There are 4 main requirements for the communication subsystem. Firstly, communication between Asclepius and ground control must be possible at all times, excluding launch and when eclipsed by the moon. A data rate of 94,032 bits must be maintained, determined from the compiled data requirements of the spacecraft. A bit error rate of less than 10 millionths must be maintained, and all communication should be modulated and encoded. Asclepius' communication system will comprise of 2 systems: a main high-gain antenna system and a secondary low-gain antenna system for redundancy. The main communication system will be comprised of a 2.26 meter wide parabolic dish operating at 20 watts with an antenna gain of 33.87 decibels and will operate at S-band frequencies and use quadrature phase shift keying modulation. It will be mounted on a gimbal such that it faces Earth at all times. A secondary communication system will comprise of 2 low-gain Yagi antenna arrays, each with 20 decibel gain operating at S-band frequencies and using binary phase shift keying. Yagi antennas were chosen for the omnidirectional nature and relatively high gain. Due to the lower antenna gain, antennas will operate at a lower data rate that only contains necessary functions and updates at a lower frequency. Next, Kevin will talk about CNDH.
The command and data handling system is required to process and distribute all data involved with Asclepius and must be able to withstand environmental conditions. Failure to do this will result in failure of the mission. At the core of the Asclepius command module will be this British Aerospace Systems single-board computer. The main qualification that this has for use in the resupply mission is the protection from radiation that can lead to software errors as well as the degradation of electrical performance or permanent failures. Programmable timers as well as a newly implemented safe mode will allow for spacecraft recovery events. With these protective measures, the spacecraft will be capable of completing the resupply mission. Changes have been made to the mission phase configurations. After figuring out that the thermal management, radio reception, and attitude control systems are the most vital systems throughout the entire mission, dedicated bus lines have been allocated to the GNC, thermal, and communication systems. Nick will now talk about GNC.
GNC must be capable of controlling the attitude of the spacecraft and have continuous knowledge of its orbit throughout all phases of the mission. It also must be able to sense its relative position and orientation to the target spacecraft throughout the rendezvous process. For attitude determination, Asclepius will use a ring laser gyro and 2 star trackers. Asclepius will have a set of 16 unidirectional thrusters for attitude control. These thrusters are placed with redundancy so that they are resistant to failure in either a stuck-on or off state. The thrusters are divided into 2 thruster groups, where every thruster in one group has a corresponding thruster in the opposite group, producing an equal and opposite moment and acceleration. Each thruster group is capable of independently controlling the spacecraft with the loss of 1 thruster. The thrusters will also be used for fine orbit control and proximity operations. During proximity operations, Asclepius will use LiDAR to determine its relative position and orientation with respect to the target spacecraft as it approaches for rendezvous, which will be verified against star tracker data. For spacecraft navigation, Asclepius will use the Doppler orbitography and radio positioning integrated by satellite system. This system will allow Asclepius to get instantaneous position and velocity data while in view of ground stations on Earth. And now Alex will talk about power.
The functional requirements for Asclepius' power subsystem was to be able to provide the spacecraft with a continuous source of power while having a primary and secondary power source to supply that power. Solar panels will be used as a primary power source. Asclepius is expected to produce a peak load of 5,420 watts of power. The table is shown as some of the power estimates for the spacecraft. We estimate that a total of 1,420 watts of power will be needed during normal operations. Triple junction Azure Space were found to be the best solar cell for this mission. Using the end-of-life power edge of 419 watts per meter squared and the required peak load of 5,420 watts, the area of the solar panel can be calculated to be 13 meters squared, but that was rounded up to 14 to count for any error. Flexible solar panels will be used because they will be easier to fit into the SLS's fairing. Space grid batteries will be used for our secondary power source. Initially, lithium-ion batteries were considered as the best type of battery for our mission. Further investigation has found that there are better batteries in development that could be used for our mission in 2033. One of those developments is lithium sulfur. Initial tests have produced good results. They can be cycled 1,500 times before they begin to degrade, and that number is expected to rise up to 2,500 times. They also have a 100% available depth of discharge as well as good temperature and pressure tolerances. Overall, lithium sulfur looks to be the future of space grid batteries. If they keep improving, ResupplionNew hopes to use lithium sulfur-based batteries for the mission. Now, Nick will talk about our thermal subsystem.
Thermal control will be responsible for keeping the spacecraft operating between 10 and 30 degrees Celsius throughout the mission. Thermal control will both regulate and monitor the temperature of Asclepius. The combination of active and passive heating elements will be used on Asclepius. Multi-layer insulation will be used to control the emissivity of the spacecraft. Louvers will allow the spacecraft to reduce its temperatures, and heaters will allow the spacecraft to elevate its heat generation. The mission will primarily occur in a lunar distant retrograde orbit, where solar radiation is the primary heating element. Solar output is expected to vary depending on the launch date, so analysis was performed for a range of solar constants. And now Takugo will talk about our scientific instruments.
Asclepius' robotic docking arm system will facilitate Asclepius to dock with the target spacecraft. The 5.3 meter long arm will use optical cameras to determine and find the latch point on the target spacecraft and will contract to predefined angles to bring the 2 docking ports together. Asclepius also contains communications and scientific instruments. A 2.26 meter wide parabolic dish antenna and a set of 2 Logan Yagi antenna arrays will be located on the spacecraft. Space is also designated on the spacecraft for universities and organizations to conduct research. Currently, 1 synthetic aperture radar will be used to search for water ice on the surface of the moon, and 1 ultra-high energy cosmic ray detector will be used to study cosmic rays away from the effects of Earth. To recap, the resupply mission will supply fuel to a crewed orbital Mars mission every other opportunity starting in 2033 and ending in 2037. This refueling will occur in lunar distance retrograde orbit and will be completed using a collapsible tank to squeeze fuel out of Asclepius into the target spacecraft. Afterwards, Asclepius will continue to orbit the moon and conduct scientific research. The resupply mission will have lasting effects on future space endeavors. In-orbit refueling is a requirement for more daring space missions, and Asclepius will act as a proof of concept. Ultimately, resupplying mission is one of the great leaps for humanity to become an interplanetary species.